This video is about the paper, A Pixel-Based Framework for Data-Driven Clothing by Ning, Yilin, Zhenglin, Geng, and Ronald Fedkiw from Stanford University. The outline of the talk is as following. We'll start with the motivation and then set up the problem formulation and introduce our methodology. After that, we'll describe the dataset, implementation details, and evaluation results. Finally, we'll conclude with some discussion on future work. Virtual clothing is ubiquitous in the entertaining industry, with many applications ranging from feature films and video games to VR and AR applications. In recent years, it has also seen huge potential in the e-commerce industry for online apparel shopping and virtual try-on applications. However, the considerations for e-commerce clothing applications differ from those from the entertainment applications, with focus on high-quality predictions with fast turnaround, low resources, and good scalability. Although there have been many advances in cloth simulation, the ability to match real cloth of a specific material, especially with high detailed wrinkling, remains challenging. On the other hand, data-driven methods, especially deep learning on large datasets, have seen recent success in many areas such as face recognition and autonomous vehicles. However, although they have shown impressive results and have low latency for inference, these data-driven models also tend to suffer from poor generalization when it comes to unseen data. To get the best of both worlds, we can combine data-driven models with physical priors to allow for more control and transparency and better generalization while remaining faithful to data and enjoy efficient inference. Thus, we propose a new framework for clothing on humans that's primarily data-driven while also embracing simulation and geometric techniques whenever possible. For proof of concept, we start with a simple task. Specifically, given input pose parameters theta, we aim to predict the 3D cloth shape x as a function of theta. Using this task as an example, we show how physical priors and data-driven models can complement each other. In particular, we leverage well-studied and robust standard skinning schemes, which procedurally compute the body surface given skeletal joint angles. During pre-processing, we pre-compute barycentric embeddings to skin the cloth mesh onto the skinned body surface, as shown on the left. The embedding weights W describe how each cloth vertex position is a linear combination of the three vertices of the body mesh triangle it is embedded into. An important benefit of skinning is that it captures nonlinear rotation, and thus lowers the complexity of the learning task. Another benefit is that this mapping between the cloth and the body surface does not have to be one-to-one, and thus we can have complex overlapping folds such as the jacket collar on the right. Now, given any new pose, we can easily skin the cloth given the skinned body surface in that pose using the pre-computed embedding weights W. Note that this is an efficient linear operation and the matrix W is very sparse. To summarize, we have decomposed the 3D cloth shape x as a function of the body pose theta into two parts. The skin cloth, x skin of theta, and the residual displacements dx from it. Since the skin cloth can be procedurally computed, we only need to learn the offsets dx, which likely makes for a simpler and smoother function. How to represent the offsets dx? Clearly, we can concatenate it as a dense high-dimensional 1D vector and train a fully connected network to directly predict it. But as this example shows, such predictions can be noisy. To recover some amount of spatial coherency and smoothness, people commonly resort to linear dimensionality reduction methods such as PCA. Indeed, the regularized network that predicts a small number of PCA coefficients show better and smoother result. Alternatively, since the offsets resemble a displacement map, we can naturally try to represent it in the image space with better spatial coherency via cloth pixels. This leads us to our pixel-based cloth framework. We let each vertex in the UV space store the offsets dx in the texture coordinate and normal directions. We can visualize the displacements by moving each vertex by dx. Since these displacements can be conveniently interpreted as RGB colors stored at vertex positions in the pattern space, we refer to these UV vertices as cloth pixels. Although cloth pixels in the 2D pattern space is amenable to learning with graph networks, we can further interpolate them to a background Cartesian grid of pixels to obtain a standard image via rasterization. Note that here we add a little padding for smoothness at the border. These cloth pixels are amenable to learning with standard CNNs, and we can easily interpolate from the learned cloth images back to the cloth pixels as well. As an aside, this pixel-based framework enables convenient shape modification via image editing. In particular, painting with a blue brush changes offsets values in the normal directions and can be used to add folds or wrinkles. To summarize, we have further transformed the problem by rewriting the offsets dx in terms of displacement cloth images. Given input post theta, we wish to predict the displacement cloth image I of theta. Then we interpolate it back to per vertex offsets dx and add to the skin cloth to recover the post cloth shape x of theta. To learn the offset cloth images, we resort to data. Ideally, we would like to learn from large-scale datasets of high-quality 3D cloth data. However, what we currently have is rather far from that. Given the limited amount of current available 3D cloth data and the challenge to build such a large-scale, high-quality dataset, we decide to start simple with a single person wearing a single garment, and we create a synthetic dataset via simulation. But we would keep in mind that the ultimate goal is to have many people in many garments with real captured data. Since we only work with one human body model, we put some care into acquiring a good scan using a commercial solution. Then we manually rig the upper body as shown here. Similarly, we also carefully construct the garment mesh via a reverse engineering approach. We first cut it into pieces along seam lines. Then we scan each piece using a scanner and reconstruct it digitally. Finally, we stitch the pieces back together. To skin the garment, we take the following steps. First, we mark a set of characteristic curves on both the body and the cloth mesh in their rest states. Then, we use the correspondence as boundary conditions and solve Laplacian equations to morph the cloth onto the body surface, and resolve any collisions using push-out. Thus, we have obtained a skinned cloth. However, the initial dressed cloth can exhibit large distortion, as we can see here. The red elements are stretched, the blue elements are compressed, and the white ones are not distorted. So we run a fine-tuning simulation to reduce distortion. Note that, although this significantly reduced distortion, we cannot fully eliminate it since the cloth is still confined to be skin-tight on the body surface. After fine-tuning, we record the embedded weights W. To sample different poses, we use uniform sampling in the valid range of human motion. Specifically, we refer to the anthropometrics guide on the NASA website as linked on the left. Any invalid poses with severe self-penetration are subsequently pruned, and here is the resulting joint angle distribution plot on the right. This slide shows the pipeline of how we generate the dataset. For each sampled pose theta, we compute the skinned cloth as skin of theta. We also simulate the cloth until static equilibrium and record the ground truth cloth shape x of theta. Then we take the pair and compute the offsets dx of theta, which we record in the 2D pattern space and then rasterize to a cloth image I of theta. The image resolution we use is 256 by 256. The dataset contains 20,000 samples, and some examples are shown here. We divide it to an 80% training set, a 10% regularization set, and a 10% test set. The regularization set is used to prevent the network from overfitting, and the test set is used for model comparisons in terms of loss functions and network architectures, and serves as a proxy for generalization error. Next, we discuss learning on this dataset and show some experiments. The learning framework is straightforward. We train a convolutional neural network model that takes input post theta and predicts offset cloth images I of theta. The predicted offset cloth image is then interpolated back to cloth pixels in the 2D pattern space to obtain the per vertex offset dx of theta. These offsets are then added to the skin cloth x skin of theta to produce the predicted 3D cloth shape x of theta. The CNN model contains blocks of transposed convolution layers with batch normalization and ReLU activation. The model is trained using an atom optimizer on both image loss and normal loss. The image loss is simply the distance between the predicted displacement cloth image IPD and the ground truth displacement cloth image IGT, weighted by a Boolean mask M of the padded UV map. Different norms such as L1, L2, etc. can be used here. The normal loss computes the cosine distance between the predicted vertex normal NPD and the ground truth one NGT. We compare different loss functions in our experiments. While L1 and L2 norm on the image loss does not make much difference, adding the normal loss indeed helps the model capture more details such as wrinkles. Using the best loss model, we see that the trained CNN can generate plausible shapes compared to the ground truth. Here are some examples from both the training set and the test set. To evaluate model generalization, we run it through a completely unseen skeletal motion capture sequence from the CMU mocap dataset. Surprisingly, the model exhibits decent temporal coherency even though it is trained on static data. Note that there are some artifacts due to different skeletal riggings. An important benefit of our framework is that it naturally supports hierarchical approaches. We can learn at higher resolution by dividing the cloth mesh and the corresponding displacement cloth image into patches, and train on each patch like this. Thus, training can be parallelized and individual networks can learn to specialize. Indeed, the models trained on patches yield lower quantitative errors and better visual results compared to the model trained on whole t-shirts, as shown here. To avoid any visual discontinuity and noise across the patch boundaries, we can use a variety of methods to smooth the stitched results. For example, one can pre-compute the PCA basis of the whole mesh on the training samples, and then project the stitched mesh onto a subset of those bases. Since the ground truth data don't have kinks at patch boundaries, the PCA basis also won't have kinks at patch boundaries unless we get into ultra-high frequency modes. Therefore, reconstructing the predicted results using a not too high number of PCA bases act as a filter to remove discontinuities at patch boundaries. In our experiments, using 2048 components leads to good filtering results. Of course, alternatively, one can explore other approaches such as GANs. Since it is often difficult to obtain accurate input body shapes for real-world applications such as e-commerce virtual try-on, we stress test our approach's robustness to inaccurate body shapes. We intentionally modify the body shapes to be too thin or too thick, and for each modified body shape, we use the same training data for cloth shapes. This merely changes the value of dx, and thus the cloth images I stored for each post data. As the figure shows, the models can learn to compensate for the errors in the offset cloth images, and predict reasonable cloth shapes despite very inaccurate body shapes. Similarly, since skinning is also hard, we stress test our approach's robustness to skinning artifacts too. We intentionally introduce skinning artifacts as shown here. Again, this merely changes the value of dx and the cloth image I for each post data. As before, the models can learn to compensate for the errors in the offset cloth images, and predict reasonable cloth shapes despite bad skinning artifacts. Finally, to demonstrate the generality of our framework, we also consider a necktie example. Unlike t-shirts, they are loose-fitting and can have very large displacements from the body surface, similar to skirts. But as we see here, the trained model is also able to produce promising results. We'll end with conclusion and future work. In conclusion, we proposed a pixel-based representation for 3D class shapes that leverages procedural skinning methods to factor out significant nonlinearities due to joint rotation and skin deformation, and thus reduce demands on the neural network. We further recast the prediction of vertex positions into the predictions of images and directly used well-studied convolutional neural networks. We demonstrated the efficacy of our framework on the task of learning 3D cloth shapes from input body pose parameters by training CNNs to predict cloth images from t-shirts and neckties. We also demonstrated that our approach is robust to inaccurate body shape or skinning artifacts. For future work, we would like to learn more from real-world captured cloth data. We will also like to generalize to a larger variety of garment types and materials and body types. In addition, we would like to explore alternative network architectures, loss functions, and training schemes to enhance the visual quality of predictions. Furthermore, we would like to experiment with techniques such as 3D CNNs and recurrent neural networks to achieve better temporal coherency in dynamic sequences, such as the swinging of a dress. Thank you.